the lecture. So I got up to almost everything. So today, just warning, there is an orange cable in the back. Do not trip. It exists now on short power, as they say. Okay, before we get started, questions? Any kind? Yeah.
Wait, so the kernel that we were looking at, F is the entire transformation, not pieces of that, right? So when
What's
we
that?
were choosing things.
Yes, we were choosing things, exactly. We
And
were
our
choosing
goal-
things in a barcode. Right, yeah.
So our goal is to send it to 0, so it was in the kernel, and
Yeah.
the goal is to do that for each piece, not to
Yeah,
get this
so-
continuous thing.
Yeah, so let me call this out. Did you have a question too, or?
Blackboard. I don't think there's anything posted.
Really?
There's two links. There's two links.
There are 2 links?
I had 2 links. I had 696 and 496. 496 was empty. 696.
It's in the 6.9. Oh. interesting.
Because Chris and I checked. So
Got
we
it,
couldn't
okay.
find any.
So I will look into that. You know what? This may be one of those situations where Blackboard is evil. Not that those ever happen. But if it's turned out that all the Blackboard stuff is in 696, I will copy it and dump it into 496. It ought to be there. Does anyone else notice the same kind of problem?
I think
Yeah.
from it, there's apparently nothing on 496.
Okay, so that must be what happened. Yeah, I will fix that.
Thank you.
You're welcome. Okay, that kind of logistics question is the sort of thing that's like, all right, I should have noticed that. And actually, they really should be linked, but I guess they're not. Anyway, okay. So, for your question, listener, we were looking at a barcode. And this is a point worth looking at a little further. So I had an example barcode that was an R2, mapping into an R2, mapping into another R2, mapping into, let's see here, R. And let's see here, I'm gonna make sure I got the same maps that you've got going on here. The first one was one, this guy, and the second one was, and the third one was, is this the same one we're talking about?
Yeah.
Wasn't that 2?
I have a
1,
2,
2.
yeah.
It was 1, 2, 0, 1,
Oh,
and 1, 0.
2, 0, 1, okay.
And also
And
this
that was 1, 0, not 0, 1.
On the far right one.
Oops. All right, I have several of these on my notes here. Okay, cool. All right, so this one. And the point was that I picked a basis kind of in a special way here. And I picked a 1, -1 here, and I picked a 0, 1 here. And made the observation that this guy ended up in the kernel, so it ended before it got there, so to speak, and this one kept going. And this one ended up at a 1, -1. And then at this point here, I picked another basis up. And I said something like, I need to pick it carefully in some fashion. And I think your question is about the care at which I'm picking it, or what would happen if I didn't
And
be so careful?
What criteria? are
Yeah,
you
okay,
using?
all right, so let's address that. I saw a hand up too, Brian.
Yeah, so the 1, -1,
This
any
guy.
multiple of that, yeah, that
Mhm.
leaves, any multiple of that is the kernel.
Right.
But doesn't, it's a 2 by 2 matrix that gets mapped times a 2 by 1, which gets mapped to a
Right.
2 by
Right,
1.
so you do row into column, and that's 0.
But how is a 2 by 1 matrix the resulting matrix in the kernel if it's not in
Oh, okay.
R2?
So this in fact is 0, 0.
Yeah, but that's not in R2, is it?
Why not? It's
Oh.
got 2 components.
Okay.
Lies in R2, it's the origin in R2.
Okay.
Does that answer your question?
Yeah, I just gotta review a little more.
That's fine. Okay, so, right, the question was the care at which I picked it, and I kind of picked these from the outset. Well, let's even ask the question, what if I wasn't so careful here? Because this Gabriel's theorem that I stated said something like that barcode is somehow representative of this thing anyway. So I should be able to be a little less careful. I was pointing out care because I wanted something, I wanted an easy picture. But if I'm not so careful, it still works. So let me pick a different guy here. So let me erase this one and say I didn't pick something that spanned the kernel.
And
Well, so at this point, this is a basis of this base. 1, 0, 0, 1 is definitely a basis of R2.
The conversions.
Right. Now, you're anticipating my next point is what happens when I multiply this vector by this matrix? What do I get? Well,
The first column.
right, which is 1, negative 1. And the problem is, at this stage here, I no longer have a basis. This is no longer a basis of R2, because both of these things are the same vector. So in some sense, what's happened is this guy here and this guy here really, well, you know, I'd kind of be remiss in thinking of them as a basis. I need to add something else to this discussion, but in any event, one of these two is redundant. So I need to get rid of one or the other of them if I wish to have a basis. So the point is that if I don't choose wisely here, I end up with a linearly dependent set here. So what I'm trying to do is I'm trying to make a choice so that I get a linearly independent set as I'm moving along. Now, if I happen to pick badly, like I did here, all is not lost. I can just say, you know what? I don't really care about the fact that I've gotten the same two vectors here, a linearly dependent set. Let me just remove one of them from discussion at this point. So in essence, what I'm going to do is just sort of cross this guy off and say, well, this bar here ended as it did in the previous one. I still need to extend my out to a bigger basis. I could be really careful about picking this, or I could be somewhat less careful and say, all I'm trying to do at this stage is extend to a basis. So I got to pick something that's linearly independent from this guy. Now, again, if I make a bad choice, I'm going to have to do the same kind of cross out at the next stage. Now, a good choice is if I've got the kernel sitting there, I know everything in the kernel is going to go away. So if I prioritize picking basis elements that span the rest of the kernel, then it kind of makes my life a little easier down the road. But it's not necessary. It'll kind of come out in the wash in the next stage. Does that answer your question?
Yeah, and so if it would have converged farther down the line, you could do the same
That's
thing.
right. That's right. Yep. Dave.
So we've chosen, we're choosing these vectors to complete the bases to maximize the length of each bar. Is that correct?
I mean, in essence, yeah. So the neat thing about this is that up to some switching like this about which one I chose, at this stage I've got a choice.
Right.
But up to that choice of, well, I pick which one of these is going to keep going and get rid of the other one, up to that choice, actually everything is constrained for me.
It can't be any longer or shorter?
No, in fact, I don't have any further control.
Okay.
In fact, that's what Gabriel's theorem says.
Okay.
And in particular, if I have some other diagram, this is one after the other after the next. If I have a rectangular grid of these guys, so maybe a big rectangular grid of vector spaces with linear maps going horizontally and vertically, the big terrifying grid of vector spaces and maps. In that case, then I do have some choice. I can pick, in some sense, larger or smaller bars, and one number of bars. It turns out that actually there's a lot of freedom in that case. But in this case here, everything's locked down. Other questions? Okay, so let's sort of pick up the story where we left off. We were talking a bit about, well, we've got kernels floating around, we've got this dimension theorem for matrices floating around, and we've got quotients. So we need to come to terms with each of those various pieces. And I want to tell a story about how specific quiver representations turn out to be especially nice. They have good properties. And those go under the name of chain complexes. So let me set this kind of diagram aside for the moment and define for you what a chain complex is. And then we'll come back and look at it as a diagram standpoint, and then we'll start to delve into it. Chain complexes are the fundamental building block of computational topology and algebraic topology in general, and something, a much bigger machine called homological algebra. chain complexes are the mathematical object of interest. Okay, so what is a chain complex? Well, I'll give you a definition. The chain complex is a quiver representation like the following. And I've got a vector space, and another vector space, and another vector space, again, all one after the other, with maps like so. Each of these are linear maps. Vector spaces, linear maps. Now, I don't necessarily care if they're all the same vector space. So this could be a V0, V1, V2, V3. Or it could go the other way, that's totally fine. In fact, I'm belying my desires to talk about cohomology at this point. An executive decision here. We're going with this notation. And I'm going to name those vector spaces. Call this one D0, D1, D2, D3. And of course, this one is D1. So a big, long chain of vector spaces and linear maps. It's a quiver representation, much like we were looking at barcodes for. But there's some additional constraints for which the bars fit together, or the bases fit together in a very specific way. And in particular, for which, if I compose two consecutive maps, one after the other, I get 0. Everywhere along this complex, everywhere along this diagram. So if I take this guy, then this guy, notice this is a little weird. You have to read it backwards, because if I'm, say, sitting at V1, I take a vector at V1, I first apply D1, now I'm in V2, and then I apply D2. So composition is kind of reverse of the arrow diagrams. Yeah?
Just concretely establish, are the D's your linear transformations?
Yep, they sure are.
And the V's are your vector spaces?
That's right. The D's are your linear transformations, i.e. your matrices, and your V's are your vector spaces. That's right. So the point is, if you do matrix multiplication of consecutive maps, you get the 0 vector out. Yep, that's right. So this is meant to be read as a 0 vector. Or 0 matrix. Yeah, actually, I guess it's a 0 matrix in this case, because these are matrices that are multiplied.
So in a sense, regardless which basis I'm starting at, after 2 linear transformations, I should be at the 0.
That's right.
Regardless.
Regardless. Yep. So this is a very particular quiver representation. The one we had up on the board a moment ago is not a chain complex. But this definition does something interesting. It fits together the kernels and the images, the kernels and the images of the consecutive maps in a very particular way. So the observation you ought to make and this is just a direct translation of this equation, is that the kernel of the k+1 map has to contain the image of the k map. So the kernel of k+1 map has to contain the image of the k map. So it's just a direct translation, but it's useful to think of it in terms of vector spaces. The image of a linear transformation is a vector subspace, as is the kernel. Notice both of these are vector subspaces of which space? you can use either one of them. The kernel, say, of this map is where? The kernel of D2 is a subspace of which? Of V2. And the image of D1 is also in V2. So both of these guys here are vector subspaces of Vk plus 1. So they're both vector subspaces of Vk plus 1. I'm essentially, rather than merely asking for them to fit together equationally, sometimes it is useful to think about it in terms of subspaces. Okay, now let's refer this back to the barcode kind of diagram. What must happen if I were to have a basis of elements, say at V1? Well, all of that basis at V1 maps entirely to elements of V2 that are going to map to 0. So what that means in terms of bars is that all of the bars cannot be longer than 2. So this means less than or equal to 2. As in, I can possibly make it from here to here, but when I make it to here, I'm at 0. So the longest the bars are ever on is 2. Okay, so you can right away pick off chain complexes in that they've got this nice property that the bars will have length less than or equal to 2. Okay, now when you've got a chain complex, you can do some things with that chain complex. For one thing, it's useful to identify if I've got a chain complex or not. How do you do it? Well, if you've got the matrices, all you need to do is some matrix multiplication. So let me give you an example of a chain complex. We can quickly verify that, yep, it is a chain complex. Make sure I've got my equations right here. So we have a bunch of matrices here. This one is on 1, and this one is here. This one is here. And let's go ahead and let's compute some matrix multiplications. So let's see, in which order do I multiply these two matrices? This is
A plus 1 equal to K.
You do the left, you multiply the left by the way, so you do 1, 1, 1, 1, negative 1, negative 1 times 1, 1, 0, 0. So the matrix underneath D0 first, then on the right, it's right multiplied by D0.
right. Let's see here. Are you sure it's right?
Well, no,
No,
right,
it's
no,
left
yeah,
multiplied.
Yeah.
Left multiplied. Because if I've got, say, a vector here,
Right.
imagine there's a vector here. It's living in this space.
Right, yeah.
Imagine this vector lives in this space. So the first thing I'm going to do is I'm going to multiply it by this matrix. First thing I'm going to do is multiply it by this matrix. Now, this product is in this space. Then I multiply that product by this matrix. Which says I need to multiply on the right, not left. Mathematicians are dyslexic. Anyway, not so good when giving directions. Actually, I'm bad with directions anyway, because although I can get somewhere, I navigate topologically. And this,
You'll get there eventually.
I'll get there eventually, although it might take a long time, which irritates the passengers.
Just don't follow us.
I had a colleague who said it's a very good thing the city is path connected. Also a topologist. Anyway, so let's go ahead and let's do this matrix multiplication and verify that we've got indeed chain complex going on at this stage. Remember, we've got to check all of the products. So what do I do? Row into column. So 1 times 1 plus 1 times negative 1. Sure sounds like 0 to me. Same thing over here. And then this bottom row is all zeros. All right, cool. So we're good at this stage. And then the next one. Again, remember, multiply on the left. And of course, this row multiplied by that column, I'm hitting a 0 on a 1 and a 0 on a 1. So this is totally fine. I get row into column, that's a 0. Row into column, that's another 0. And I've got board collision. Okay, so those are the two sets of consecutive maps, so we're totally good. Worth noting, usually when people are writing chain complexes, you know, I wrote out a big, long, infinite long string of them. You can, without any hazard, extend with a 0 on the end. What matrix must this be? A 0 matrix. Similarly, over here, what map must this be? Again, another 0 matrix. You have no choice once you put a 0 there. Does this mess up making a chain complex? Well, I compose this map with this one. It doesn't matter what this one is. I get 0 because 0 multiplied on the right of any matrix over here gives me 0. So that's going to check out. Similarly, over here, if anything I put here multiplied with this map is also going to be 0. So it causes no trouble to extend by zeros. Okay. Now, it is, of course, important to realize where you're starting, if this is a 0 or a 1 or what have you. Totally fine. Okay, so that's a chain complex, and of course, part of the reason why I picked the other barcode diagram that we were looking at, that wasn't a chain complex. It had a little different structure. You can see it from the bars that we had drawn before, but it's worth just checking that, yep, the compositions don't work out to make these 0 in all places. So the one that we had, which was a 1, 0 here, and a 1, 2, 0, 1 here. This guy's not a chain complex. Reason being, well, at this stage here, it's fine because this map times this map is definitely 0. But what about this map times this map? So let's do it out. Let's see, row into column, what's that? That's -1. -1's not 0. So I don't care what any of these are. Whatever it is, it ain't 0. So it's not a chain complex. And in particular, when we looked at the barcode diagram, we had a bar that started here that went longer than 2. Another indication we don't have a chain complex. Okay, cool. So chain complexes are kind of handy that way in that they've got these short bars. Now, the reason why I stated something about kernel being a subspace of an image in here is because I'm preparing us to make use of the quotient machine. And the quotient is something that plays a very important role. And the reason for that is not even immediately apparent. So let me first give you a very special kind of chain complex. And then we'll notice that the way to tell when you've got that special chain complex from when you've got a normal chain complex, sort of run-of-the-mill one, comes about with quotients. So we'll circle back and we'll pick up the quotients. So these special chain complexes are called exact sequences. Terminology is historical, and people go with this. So, definition. An exact sequence is a chain complex in which, well, now we're going to actually use the spaces, where the kernel of k plus 1, this guy, it doesn't just contain the image, it is the image on the nose. So it's not just proper containment, it's equal. So it's a much stronger condition than chain complex. It is a chain complex because if this happens, of course, you compose consecutive maps, you get 0. But this is a lot stronger in the sense that now, once I know what the kernel of this map is, I've now completely locked down what the image of this map must be. Now, additionally then, there's a lot more that I know. This is very constrained. Once I've locked down the image of this and the dimension of this guy, that tells me exactly what the kernel is, so I've locked down the next guy. So the moment you know all the, if you know all the dimensions and you know one of these things here, a whole bunch of constraints snap into place. Exact sequences are therefore what we might call very rigid. The structure is highly confined. Now, exact sequences can do really cool things. In particular, exact sequences are really awesome for computing stuff. And they generalize this notion of the dimension theorem, the rank-nullity theorem that we mentioned last time. Rank-nullity theorem, you sometimes hear this called the dimension theorem for matrices. Or sometimes you hear it called the fundamental theorem. Of linear algebra. If you really want to get pedantic, there are slight differences between exactly what each of these theorems are supposedly saying, but morally they're really all talking about the same thing. The idea is if I have a map, and a linear map, then I can take apart the domain by looking at all the stuff that's sent to 0, i.e. the kernel, and everything that isn't, the rest of the kernel, the rest of the non-kernel, so to speak, and I can identify that non-kernel stuff with the image, that in fact they're isomorphic. And then there's some stuff left over, which was the co-kernel that I mentioned. So the idea is very special thing about linear maps. This is not true in general maps. The idea is if I have a linear map, is that really this thing here is isomorphic to the kernel plus the image. And this thing over here is the image plus the co-kernel. We talked a little bit about the co-kernel last time, and I'm going to bring it up now with exact sequences because you can really see how this thing fits together.
Isomorphism is a
Vector space isomorphism means it's got a one-to-one onto mapping that is itself linear, and as a result, its inverse is also linear. So one-to-one onto mapping, which is linear, will in fact be an isomorphism.
Is that the same thing as saying it's operation preserving?
The linearity is operation preserving. Yes, exactly. So linearity is, if you will, linearity is vector space structure preserving. Preserves the structure of the vector space when you pass through the map. So this is saying, from the purposes of linear algebra, you cannot distinguish. Take a basis of the kernel, take a basis of the image, concatenate those bases to make one big long basis. That vector space you can't distinguish from the domain. On the other hand, if you take the image of that, take the co-kernel of that, whatever that happens to be, stick those guys together, concatenate their respective bases, you end up with the codomain. Okay, so this is fundamental to the way linear algebra operates. And in particular, you can see once you've locked down the image, it plays a role on both sides. You lock down the image, it plays a role on the domain and the codomain. And whatever is left over is either getting sent to 0 on this side, or never cropped into existence on this side. You never got to it. Now, how does this show up with exact sequences? How are they doing anything useful like that? How do they generalize this notion? Well, what do I have over here? I've got a kernel and I've got an image. Well, what does this mean? This means the kernel of one map is the image of the next. Okay, so let's build an exact sequence with just 3 maps. let's stipulate that this is an exact sequence. Let this thing be an exact sequence. Now that I've stipulated this thing is an exact sequence, I'm going to make use of the fact that I know that D0 and D1 are both linear maps. And therefore, they tell me something about the respective structures of these three vector spaces. And I can tear them apart in various ways. See, I can tear this domain here apart in terms of the kernel and the image of D0. I can tear apart V1 in terms of the image and the co-kernel of D0. And I can also tear it apart in terms of the kernel and image of D1. I have some freedom there. Yeah?
Should that not be the pre-image of F? Kernel of F, O plus pre-image of F? Right now,
That thing?
no, over there.
Here.
Pre-image of F.
Pre-image of F.
Because the image of F will lie in W, but that may not necessarily lie in V, right?
Hence the isomorphism.
Okay, right.
Yes, you're right. This is not a subspace of V.
Right.
This is not a subspace of V. It's isomorphic to V. It's the same. It is the same vector space information. These are both recipes for two otherwise indistinguishable vector spaces, but as sets. One is not the subset of another. That's really crucial. I'm not, and in this case here, it happens, which is a little confusing, that both of these guys are indeed subspaces of this one. But it's not true. It's not the case over here. And in fact, this is the place where, when you're doing linear algebra for the first time, this is the place where the magic happens in some sense. Because they're two separate spaces that really don't feel like they have anything to do with each other, but they do. Okay, so let's decompose this exact sequence in terms of that kind of decomposition. So over here, I've got the kernel of D0 and the image of D0. Now, what happens on the other side? I've got the image of D0 and the co-kernel of D0. But I could have, this thing is then the same thing as, because it's the same thing as V1, it's the same thing also as the kernel of D1 and the image of D1. And that maps right along, that maps over to the image of D1 and the co-kernel of D1. No, we're running out of room there. So I've just decomposed this first map and this second map according to this isomorphism theorem, the Rank-nullity theorem, the fundamental theorem of linear algebra, whatever you want to call it. I've torn it apart in that way. Now, I haven't used the exactness of this sequence. I've just used two linear maps and no further information. Now I get to use the exactness. What does the exactness say? It says that the kernel of D1 is the image of D0. Oh, well, look at that. Kernel of D1 is the image of D0. They show up together. Well, that's kind of interesting. What does that tell me about the co-kernel of D0 and the image of D1? They must also be isomorphic. That's right.
What do isomorphisms say about surjectivity and injectivity?
Okay, so an isomorphism, let me put that definition up on the board. A linear map F from V to W is an isomorphism precisely when it is bijective. And that is all. It is an I. So there's three key components to this. There's the linearity. There's the injectivity, which is in particular that the kernel of f is trivial, and it is surjective, which is that the image of f is done. Yeah.
Also, it's been a while for linear algebra. Can you show me what the plus circle?
Okay.
does?
So
I mean,
plus,
just in an
yeah.
example.
So what the plus circle says is it says take a basis for this guy
Okay.
and a basis for this guy,
Okay.
and take those two lists and stick them together
Just in one vector.
in one big long list. So basically, what this means is I'm taking, if this guy is dimension n, and this guy is dimension m,
And
then this whole thing is at dimension n plus m. Yep. So I'm just concatenating bases.
So for example, if you have a 2x2 basis for vector space A and a 2x2 basis for vector space B, you have what, a 4x2? Or 2x5, I forget which one comes first now. 4
well-
wide and 2 high?
Well, yeah, I mean, it's in essence that idea, and I'm talking isomorphism, they're the same thing. Yes. Okay. All right. The point is that it gives you a nice decomposition. What you should imagine, the picture that I keep in mind, is not a two-dimensional picture, but a three-dimensional one. Think of this as the plane, and this is a line sticking out of the plane. What am I spanning if I've got the plane and a line sticking out of the plane? I'm spanning 3 dimensions. Because I can move anywhere in the plane, and then I can move off of the plane. That's the right picture for this kind of construction. So I'm adding on a new basis element, say, out of the board. Okay. So, what does this tell me? If I have an exact sequence, it tells me not only the images and the kernels line up, but the co-kernels and the images line up also. That's kind of handy, and it's going to tell me some more information. Because if I start stringing these guys along, do some cool things. In particular, let's see what happens if I take this and write it out, and then start asking what happens when I make specific things happen to either D1 or D0. So I got the kernel of D0 and the image of D0. And that's mapping into, should I pick kernel or should I pick image? I don't really care, but I need to pick one of them. I'll pick kernel. Kernel of D1. And then again, what this is saying is pick the kernel of D1. It's the same thing as the image of, or rather the co-kernel of D0 is the same thing as the image of D1. And this thing is going to map into then the image D1 plus co-kernel of D1. Okay, and again, word collision. Okay. So the interesting thing about this, then, what does this tell me? Well, at this stage here, what is this telling me? It's telling me that all of the action, all of the interesting behavior is amongst the kernel and the co-kernel of this map and the co-kernel. So the kernel and the co-kernel of these various maps fit together as I'm stringing them along. Now, what happens then if I do something really special to D1? Because you can see D1 is all over this thing. D1 is all over this. What happens if I assert that D1 is actually 0? It's the 0 map.
The image of D1 is then.
Yes, that's right. The image of D1 is 0. Image of D1 is 0.
So we get the kernel is mapped.
Right. So let's follow this through. So the kernel of D1 is what? All of which map? All of which space?
V1.
V1, right. If D1 is the 0 map, it sends everything in its domain to 0. That means everything is a kernel. So everyone see that. If I'm sitting on D1 and I made D1 0, now I'm asking what is the kernel of this map? Well, it's everything, because everything's gotten sent to 0. Okay, so the kernel of D1 is everything. What's the image of D1?
0.
0.
Yeah.
Something like add on 0. What happens if I add on a basis that doesn't have any elements in it? Did I change the space?
No.
No, not at all. So I don't bother with it. Now what happens over here?
Wait, why is it an arrow, not an isomorphism?
Where?
So you go from
Oh.
kernel D.
Maybe I'll write it like this.
But so when between kernel
Yeah.
kernel D0 direct sum image D1. No, 2 lines lower.
Oops.
So you go from
Oops.
there
Ah.
to V1.
This is a mistake. This should be D0. Sorry. This was not supposed to change.
Okay, but that guy maps to V1.
These guys-
It's not that it's isomorphic to V1.
Oh, we'll get there. Yeah.
Because we're still using the trash.
Right. We're still using the. So I just copied it down here. I was supposed to copy it down here, and I failed.
Okay.
That's the same map.
Uh-huh.
And now what happened over here? This is V1. This is 0.
Oh, sure. Okay.
So this vector space is really just V1. Okay, now what happened over here? What else do I know? What do I know about the kernel of these various spaces? What do I know about this? Well, I know a little bit more here yet. I know what's the image of D1?
0.
That's 0. Okay, so that's kind of boring. And then I've got a V1 here, right? Or a V2 rather. Yeah, I've got a V2. Okay. Now this is just rewriting what I've got over there in sort of a funny way. But the reason for this decomposition is kind of useful. Let's take a look at what this matrix looks like. What does this matrix look like? Well, really, remember how am I making this space? Concatenating bases. So if I take a look at a matrix here, really I've got essentially 4 pieces of information I need to specify. I'm going to come from the kernel, D0. I've got the image of D1. I've got all of V1 over here, and I've got nothing there. So in essence, when I concatenate these bases, and I start figuring out what this linear map ought to be in this big, long basis.
Did you mean for an image of D0?
Once again, I meant the image of D0. Gosh, that's right. Okay, so these are going to be a whole bunch of columns of this matrix, one for each element of the kernel D0. My linear transformation is going to map along all of those columns. Similarly, this is one column for each element of the image of D0. And they're going to end up as being decomposed as a vector that's spanned by a bunch of elements in V1, and a bunch more elements that are spanned by over here, but in this particular case, it's 0. Good with that? I'm seeing some somewhat less happiness here.
So this matrix that you're drawing here.
Is this map here, written in the bases that I've written here. So rather than writing this, what was this? This is originally D0, right? This is originally D0. But written not in the original basis that I didn't specify a basis here to write down D0. But now by choosing this kind of decomposition, I'm now thinking of a certain kind of basis. A basis in which the first few basis elements all lie in the kernel, and a basis in which the rest of them don't. Now, if that's the case, then, when I make my map, these are all going to be a whole bunch of zeros in here. And this is not going to be a whole bunch of zeros, because this is everything that was not mapping to 0, it's going to map over to here. And in fact, this is, whatever this thing is, this is something that has full rank, which is to say that the kernel of this portion, this little submatrix here, is trivial. Because I've got the kernel, it's all over here.
When you say trivial, it's 0.
It's 0. It's the 0 vector space. And of course, In this particular case here, I don't have any 0 going on, so this is it. Oh, what does this tell me? What does this tell me? Well, this tells me something kind of special, doesn't it? This says that the image of D0, full rank, maps entirely onto V1. The image of D0 maps entirely onto V1. Put another way, D0 is surjective.
So every time you've written an arrow on the left-hand side of this board, that is D0?
This is D0. Yes, I should have said that. This is D0 here, and this is D1 here.
And what about the next arrow?
This is D1, and this is D1.
Okay.
Because we're following them from the.
That's right. We're following the diagram.
Yeah.
We're following the diagram along. So this ends up saying that, in fact, when all is said and done, if I have an exact sequence and I've dropped in a 0 here, this means the previous map is surjective. So if I've got an exact sequence and I drop in this D1 spot a 0 map, it means the previous map is surjective.
1 to 1?
Onto.
All right.
Onto. And look at it. What did we find here? We found the image of D0 is mapped full rank onto V1. It's onto. Now, similarly, yeah?
Quite a restriction.
It's quite a restriction. Now, similarly, as was just noted, this was one of the homework problems. There are several others such in the homework that this is a model for. In the homework, you're supposed to prove that if I were to make this guy 0, then it forces this guy to be injective. And if I make a longer sequence, and I make one before and one after both 0, then it forces the guy in the middle to be both injective and surjective, i.e. an isomorphism. So exact sequences are very powerful in that way. They're very useful tools for inference about the structure of matrices. And that's why they're very powerful. They're very good that way. Now, that's all pretty well and good, but now what happens if I've got 3 of them? One, the next, the next. So I have a sequence of 5 maps. The very first one is 0, and the last one is also 0. That's not in the homework. So the homework, you deal with 2 maps, one after the other, and then 3 maps. What happens if I've got 4 maps, or 5 vector spaces? Well, something interesting happens. Something interesting happens.
Oh, we have like an odd number.
Well, this particular kind of sequence happens enough that people give it a special name. So suppose I have 5 spaces. The first and last are 0. So 5 spaces, the first and last are 0, 4 maps. 5 spaces, first and last are 0, I have 4 maps. And this is, I'm going to assert this is an exact sequence. This goes under a special name. This is sometimes called short exact sequence. Even though the other ones were shorter, this is the other guys were shorter, but this is what is deemed a short exact sequence. Well, what do we know? Well, we label this guy as D0, this guy as D1. We already know D0 is injective and D1 is surjective. So we know, at the very least, D1 is surjective, D0 is injective. We know that. We just proved this, and you're going to prove this for your homework. Now, what's the relationship between these various spaces? Well, it's not immediately clear, but with a special name like this, you ought to suspect that there's a good reason for doing this, and something special happens. Let's, again, tear these apart in terms of kernels and co-kernels. So in this special case, we had that same construction I had on the board a moment ago. So I had what? What was our decomposition? I'm going to make use of my space a little carefully here. So I've got 0 maps into, let's see, this is in terms of the kernel of D0, direct sum the image of D0. This is D0. Then this guy here is in terms of the kernel and the image again also. So this is the image of D0, direct sum of co-kernel of D0. But that is isomorphic to the, wait, did I get this wrong? No, I'm all right. The kernel of D1 and the image D1. And I know by exactness that these guys here are the same thing. So those are isomorphic. So that's V1. Now here's D1, and I've got something going on here. This is what? This is the image D1 and the co-kernel of D1. All right, so I've written out this big long diagram broken up like this. The stuff in the box here, this is isomorphic to that. And so as a result, as are these, this is what we know isomorphic by exactness. Now, but we additionally know some other things. I said D0 is injective. So that makes the kernel of D0 go away. Now I know D1 is surjective. What does that mean about this decomposition here?
Image of D1 is
It's
all V2.
all of V2, yeah.
So the co-kernel is 0.
That's right. So let's state that again. We know that this D1 map is surjective, so the image of D1 is all of V2. Now this space, V2, is this decomposition here. Here's the image of D1, which is all of V2, so this thing better go away. There's no co-kernel. Okay, so what does that tell me? Oh, well, that tells me something kind of interesting. That I've got the image of D0 here, I've got the image of D1, image of D0, image of D0, image of D1, image of D1. I could write this whole diagram in terms of images. So let me do that. This is now image of D0 plus image of D1. What I'm doing here is I'm grabbing this guy, this part, and this part, because I realize that these guys are isomorphic. So up to isomorphism, i.e. changing the bases of it, I can just grab along like this. Then I got D1 going on here, and I got image of D1. So this is just a rewriting of this based on the fact that I know I've got an exact sequence. Well, that's kind of interesting. What do you think that matrices here with this now very carefully chosen basis looks like? Well, first off, what shape is D0 in this? Well, it's image of D0 getting mapped to image of D0, and then this other stuff over here, which is not in the image of D0.
So you're going to have the left.
Yeah, so it's going to be in this form here. This is basically D0, and this is like, what else? Stuff. Now, what happens over on the other side? Well, it's a different shape, because I've got more columns here. This space here has more columns than either of these spaces, or at least as many columns as this one, and at least as many columns as this one. So this is the image of D0 stuff. Now this is an exact sequence. So what happens to the image of D0? It's in the kernel D1. So this is a big 0 matrix. There's D1.
And then multiply those matrices, they have to be 0.
Right. So what does that tell me about this thing?
It's also 0.
Well, yeah. Because I'm going to go row into column. All right, cool. So what is this doing? Well, what this has done is this has told me that this space in the middle is really the concatenation of one space and the other. Take the space on the beginning, take the space on the other end, and just stick them together. That's what ends up in the middle. So when you have a short exact sequence of vector spaces, in fact what happens is I take the middle space and it's formed just by taking the two other spaces and sticking them together. So here's the board, here's out of the board. This thing is now the root. Cool. Yeah.
How do you know that D0 is going to be injective?
How do I know that D0 is going to be injective? You're going to have to prove that for your homework.
Oh,
That one is going to be surjective.
This one.
yeah.
So we just proved that on the previous board.
Okay.
That's the question.
But real quick, what's the kernel? Everything. Kernel of this map is everything. That is the image of this map, hence surjective. So very briefly, although we tore it apart using the fundamental theorem of linear algebra to see all the pieces and moving parts. In particular, choosing very opportune bases. Now, this sort of decomposition is kind of handy in that it allows you to think about V1 and V0 and whatnot. Now, V1, V0, and V2 as vector spaces abstractly don't really have anything to do with one another. They're just different vector spaces, and I've got some linear maps. Now, what I could, however, think of D0, what does the image of D0 look like? It looks exactly like V1, because V1's injective. It looks like an exact copy of V1 sitting inside V0, exact copy of V0 sitting inside V1. So you could think of, in fact, you could think of what this portion of the diagram is doing, the V0 and the D0, the space in the map, the space in the injective map, is as picking out a particular subspace of V1. And then V2 is whatever's left over. In this particular way, the right way to think about this is to say that V2 is actually, we've mentioned quotient at the end of last class. V2 is the quotient V1 divided by V0. Let me write that down. And here's what I'm going to do. I'm going to summarize what I'm just in the midst of erasing. Hopefully it's made it into your notes. And I'm going to make the observation that this space is isomorphic to V0. Tack on, or concatenate with, or direct sum with V2. Now, if we're in this particular special case where we've got this short exact sequence working for us, I can think of V0 as being a subspace of V1. V2 as being a subspace of V1. But of course, neither of these are subspaces of V1. So notice, are not subspaces of V1. But D0, V0, it's isomorphic to V0, and 0, V0 is a subspace of V1. In this particular situation, so proposition, the proposition is then that if I form the quotient that I defined last time, and we'll revisit that definition in a moment, if I form this quotient of a vector space and a subspace of that vector space, I get isomorphically the same thing, V2. I get the other part of this picture. And in particular, that's due to this particular decomposition. So when you want to think about what quotients are, the right way to think about them, what this proposition holds for you, or what it says, is that when you want to think about quotients, write down a basis that includes the subspace you're interested in, and everything else. The quotient is the everything else. Now, those of you who have played around with abstract algebra will know that quotients are a lot more subtle than that when you don't have vector spaces. Particularly, this argument that we went through to find that this is a direct sum, thumbs down, doesn't work. This proposition is still true, though, but for a somewhat more subtle reason. And that same subtle reason works to make this proposition work, but it's a lot more work. That's why we do everything with vector spaces, because this comes right out and we can walk through in this very intuitive way. Okay, so let's address this proposition. And in order to do that, we need to think a bit about quotients. So, recall. If, let's see here, if I need some more vector spaces. Let's say W is a subspace of V, are two vector spaces, and W, a subspace, is a subspace of V, quotient W is, well, it's the set of all, it's a set of sets. Little v plus W, and V is in V. So the thing to realize here is this is a set. And this guy here, this is just a vector. And what I mean by a vector plus a set, let's just take all the possible sums where I've got a vector and another element of W here. That's a big set. So the whole thing, this whole thing, is a set. And in particular, what set is it? It's V plus W, where W is in.
Left coset?
It is.
Yay.
It's also because we're dealing with an abelian group or right coset. Very, very handy. And that actually that's why this isomorphism works out so nicely. If you didn't have that, you'd be in trouble. Indeed. Right. So left coset, right coset are the same thing. So this is automatically a normal subgroup, etc. Yeah.
Two questions. For my mind's sake of relaxation, can I think of Euclidean space as the vector spaces?
Absolutely.
But we mean like
Absolutely.
space.
So I've got here, again, this works very nicely in 3 dimensions. I've got 3-dimensional space here. We're in 3-dimensional space. And I've got a plane, some plane going through the origin. Let's say the origin is right by the thumb. So here's a 2-dimensional subspace of a 3-dimensional space. What this proposition is saying is it's saying that if you wish to figure out what the quotient is of 3-dimensional space with this plane, what is it? Well, I form a basis of the plane, so say a vector this way and a vector this way. So there's my 2 dimensions. That's not a basis of R3. Extend it to a basis. So point off of my notebook in some way. That now is a basis of R3, isn't it?
2 or 3. Did you make a new vector? Or did you
1 vector, 2 vector, and 1 more new vector. Then what this particular theorem is saying, this proposition is saying, is that in fact that quotient of the whole space, quotient the book, is just the new vector you added. It's just the new vector you've added, which hasn't shown up in discussion quite yet. Here's the original guys and the ones you've added. Now, why does that work? Well, these cosets, what do these cosets look like? Here's my thumb again as the origin. Well, what am I doing? I'm taking the set of all points in the book. And what am I doing? I'm adding a vector to them. So what happens if I add a vector that's in the plane? Well, the plane shifts, but it's the same set. So they're indistinguishable as sets. If I move, say, this way, it slides this way, it's still the same set. But now what happens if I move off of it? Move in some other direction? I deflect off. I get a new set. Now, if I go this way versus this way, do I really go anyway? Well, I move here, but I might have a sort of a translation and a slide. Again, I can't tell the difference between all of these sets. So there's only one parameter that tells me the offset. The offset that's, in fact, perpendicular to this plane. That's what all of these cosets look like. These cosets are just merely translations to parallel planes. So the right thing to think about here is I'm building up all those parallel planes. Now, the beauty of the abstraction here is I don't have to be in 3 dimensions. I can be in 15 dimensions or whatever. I don't care. The same construction still works. So why does this play out and give me the thing that I want? Well, really, here's the long and the short of it, is I need to build a map that implements this isomorphism. Oh, well, that map that implements the isomorphism, the thing that makes this isomorphism tick, it's sitting right in front of us. It's D1, in fact. It's the idea of the proof. The idea of the proof is that this isomorphism is in fact D1. But it's D1 with a restricted domain. It's D1 with restricted domain. And in particular, in this context, then D1 has a special name. We call it the canonical projection. Basically, what it's doing is it's throwing away, here's my notebook model again, it's throwing away all of the vectors that are in the notebook, projecting them all out, projecting them onto this direction here. Just taking everything and squashing it down. Taking all the vectors in the plane and squash them down onto this line. It's a canonical projection. Okay, so that's the idea of the proposition. Let's see if we can make that happen. Okay, so let me move it up. And in particular, that statement, it is D1, of course, is not quite precise, because this is not in the domain of D1 at all. So I have to make that work out for you. And the way to do that is to build up a construction here that lets D1 do the right thing. So what do I have to do? Well, I have to ask myself, what does D1 do to cosets? So what if I have a coset?
Sorry, do we need to know the definition of a coset?
This thing.
It's just
That
any
thing.
such thing.
Yep, set plus an element.
Okay.
Yeah, sorry, I didn't say that, but coset. All right, so this thing is a coset. Or just think about it as a parallel plane. What does D1 do to these planes that are parallel to the thing I'm quotienting by? Well, the thing I'm quotienting by is D0, V0. So these particular guys here, what do the parallel planes, what happens to them? When I hit them with, oops, D1. Oh, wait, that's a verb. D1, do, that's an O. Font fail. Again, I want my LaTeX chalkboard, so I can write it precisely here and have it come out. Anyway.
We could just get like hundreds of iPad Pros.
Yeah, but still, the handwriting to LaTeX is not so good. In fact, it's bad. Anyway, so what does D1 do to this sort of vector? This is a set. There it is, a set. What does D1 do to that? Oh, well, let's find out. Let's just D1 it. Ah, it's linear, right? It's linear. D1, V plus, D1, D0, V0. Well, I know something about this, don't I? I know something really important about this.
The right-hand side is 0.
I wouldn't say the right-hand side is 0, but I'd say this term is 0.
Yeah. Because
It's a chain complex. So
Yeah,
this is
right.
0. This may not be.
Yeah.
Don't be overeager here. All right, this is 0 because we have a same things. So what D1 does is it's just the same thing as whatever happens to here. It doesn't see the V0 thing floating around. Now we know something about the image of D1, right? What do we know about the image of D1? We just wrote it up on the board previously. Yeah, we know. Now, what about the kernel of D1? What's the kernel of D1? So we know it's surjective, because I want to make this D1 do the thing here. It's surjective, okay, fine. What about injectivity? Is D1 is the sort of D1 acting on this thing injective? What is the kernel of D1? No, it's not injective necessarily, at least not necessarily. But we know something very special about it. Let's solve this equation. Let's solve the equation that Dave was implicitly proposing. Let's solve that equation. What V's do I have to pick here? Oh, well, wait a moment. I know something about the kernel of D1. What is it? It's the image of D0. Because it's exactly the image of D0. Well, what does that tell me? That tells me that the only things that end up, that spoil the game for injectivity are all the things that aren't in the image of D0, i.e. everything that's left. So, this means that, again, because of exactness, that the kernel of D1 is the image of D0. This means that if, in fact, I ended up in the kernel of D0, then this means something special about you. D plus D0 plus V0. Where does this thing lie? It's an element of D0, yeah, that's right. It's in the image of D0. Image of D0. Oh, wait a moment though. Is the image of V0 a vector space? Well, the image of a linear map is a vector space. So, like closed under addition stuff, thus, this means V is where? It had to be because of closure. So that means that this V, if in fact we've got this thing mapping to 0, it means the only way this could happen is if V started out in D0 to begin with. Now, what else is in that same coset? What else is in that same coset? So I've got a set, and I know, let me take my notebook. Here's my notebook. I've got a set sitting there, and I know that I've taken this guy and I've mapped, that's this plus some vector space. Right? So my V is here, say, and I'm adding this guy, shifting it over here, and I knew this mapped to 0. But I said that the only way that can happen is if this vector actually lies in the plane. That's what I've argued here. So the only way this guy here, this V, were chosen to make this thing map to 0 is if that V started out of the plane. So I haven't moved the plane at all. This is the 0 vector. This in fact says, I've argued then, that D1, when I'm thinking about it restricted to just the part of D1 that sort of quotiented out, as in this particular coset that goes to the origin, the only way that that can really have a kernel is if that kernel is, the kernel consists of exactly this trivial coset, the coset that goes right through the origin. And therefore, so thus, coset in question, what does it have? Has V plus D0 of V0 is, in fact, D0 plus V0, which is 0. It's the coset with 0. That means, in particular, thus, D1 is injective on this coset. Is injective on the cosets, rather. On cosets. Cosets of this form. So D1 is injective on cosets. We know it's surjective by this argument we just did. Injective, surjective, therefore isomorphism. And therefore we're done. So in fact, we've established that the quotient that can be thought of as merely the additional basis elements. Which brings up the reason why when we were building out these barcode diagrams, that at each stage I had to extend the basis. What was I doing? I was examining the contents of the quotient. And that is all the time we have. And it is worth noting, if you look at homology, and what's the difference between a chain complex and an exact sequence? Basically a quotient. And that quotient goes under a special name. It's called homology. And we'll talk more about that next time. So, see you then.